Good afternoon, everybody. I hope all of you are fine physically, mentally, and take care of yourself and each other in these hard moments. So today our guest is Mr. Joseph Ahern. He is a PhD student in the University of Idaho in the US, and he has a bachelor's degree in physics and philosophy from the University of Illinois. So today Mr. Ahern will give a talk on gravitational interactions among small Saturnian co-orbital bodies. So please, Joseph, the podium is yours. You can share your screen and start your presentation. Thanks.
Thank you. Yeah, so today I'll be talking about gravitational interactions in two different spots among Saturn's rings and moons. And so just as a general overview of the Saturn system, first, we have the main rings are the A ring and the B ring. And then after we started sending out spacecraft to the outer solar system, we discovered some of the other faint rings. We have the C ring, D ring. The E ring is largely associated with Enceladus here, which is spewing out material. And then the F ring on the very outer edge of the A ring, and then the G ring. So that has been, they've been named in the order of their discovery. So it's not really in any, in order of how far they are away from Saturn or anything, unfortunately. But I'll be talking about two different locations in these rings. The D68 ringlet, which is on the inner edge of the D ring, and then Aegaeon's ring arc, which is part of the G ring. So first we'll take a look at the D68 ringlet. You can see it's this narrow ringlet here, about 67,600 kilometers from Saturn's center. And if you round that up to 68,000, that's why it's called D68, part of the D ring, about 68,000 kilometers from the center of Saturn. So in 2014, all of a sudden, we started seeing bright clumps in the D68 ringlet. You can see that this is brighter. I'll flash back to the previous one. Here, the ringlet looks about all the same brightness. And then in 2014, these bright clumps appeared, 4 of them. And they were about relatively the same space apart from each other. As you can see in these plots, these are showing on the horizontal axis the co-rotating longitude in degrees, and the vertical axis is brightness. And so you can see these different peaks in brightness corresponding to clumps, and they appeared in 2014, and we kept seeing them all the way to the end of the Cassini mission in 2017. So as far as we know, they're still there, but we just haven't been able to see them up close ever since the Cassini mission ended. And each clump is most likely associated with a source body. And so these clumps were labeled T, M, L, and LL, which stand for trailing, middle, leading, and leading. So that was the mnemonic we used for these clumps. And then because they're about the same angular distance apart from each other, I started wondering if they were in some sort of stable configuration of a co-orbital satellite system. And these stable, stationary, compact co-orbital configurations were first studied by Salo and Yoder in 1988, same year I was born. And you might be familiar with this n equals 2, perhaps 60 degrees apart, that is similar to the Lagrange points, the L4 or L5 Lagrange points. This is analogous in a system with two massive bodies, a test particle at one of these 5 Lagrange points would orbit the primary in the same amount of time as the secondary. And the L4 and L5 points are the stable ones. And the test particle that's placed near 4 or L5 points would oscillate around that location. And these are 60 degrees behind or ahead of this secondary. But as you can see, 60 degrees is also the angular separation for equal mass co-orbital bodies. These are all of these are for equal masses. So a Trojan at L4 or L5 could be the same mass as the secondary. Of course, then it would not be a two-body system, but a three-body system, but it would still have that same angular distance. But anyway, if we increase the number of co-orbital bodies and go up to 3 and then to 4, we can see that the angular distance between them begins to get smaller because they are contracting inwards. And so with 4 clumps, if we go up to 4 co-orbital point masses, modeling them as point masses now, we would expect their angular separations to be 37.4 degrees between the middle two, and then 41.5 degrees between a middle and an outer. It's also on this side as well, if they were to have equal masses. So of course we shouldn't expect their masses to be exactly equal. Can we make their masses a very specific, unequal, but comparable mass, and make their angular separation equivalent to what we observe in the D68 ringlet among the clumps? And so that was the first question. Fortunately, there was a study in 2004 by René and Sicarli that allows us to take a co-orbital system and take the angular separations between them, plug them into this function. The angle phi here would be the angular separation. So 29 degrees or 32 or 26. And you plug those into this function and spit them out into this matrix. This is an anti-symmetric matrix. So when you solve it, you will get one row of all zeros. But that means we can just assume one of these masses is 1 and then solve for the other masses. And so we can solve for the relative masses that would correspond to a stable configuration in this system. So when we do that for just these 4 co-orbital bodies, we don't get any solutions that make sense physically, because we get one mass that is pretty much equivalent to 0. I put it in as epsilon here because it depends on which mass I selected to give it a value of 1 and then solve for the others. Sometimes this first mass gave me a very small negative mass, but within machine precision. So like 10 to the minus 17, something like that, and also negative. So that's not a physical solution. And then these other masses are just normalized so that their sum equals 1 here. But in general, we have no solutions for 4 co-orbital bodies with these angular separations. So then the question is, well, what if there is a 5th co-orbital body that we just didn't observe? Is that possible? Using the same methods of René and Sicarli in 2004 with the matrix, we do find physical solutions for a 5th co-orbital body at certain longitudes that are about 33 degrees ahead of the leading body, or I should say leading, or about 32 degrees behind the trailing body, with here with orbital motion going counterclockwise. And there's a range of longitudes where it works out, and then it doesn't work out anywhere else. in that same orbit. And this looks good because there's some symmetry here. And so we can look at, if we have a fifth object, which we'll call object 5, at one of these longitudes, what would the relative masses be of all those other objects? And so we can find solutions, and it looks pretty symmetric here too. So that's also a good sign. This fifth object, if it were farther away from the compact configuration, but still in that range that's allowable, it would have to be the most massive body. So then it would be a little surprising that we didn't see it, perhaps. But as we get closer, so this horizontal axis corresponds to the co-orbital longitude of object 5, supposing it exists. And the vertical axis is just the relative masses between these 5 bodies, as modeled as point masses. And so you can see that there is a trend. When it's more compact, we would get, so the arrows indicate the direction of orbital motion. The first, third, and fifth bodies would be more massive than the second and fourth bodies. If the configuration is less compact, more extended, then the 4 would be relatively similar, but then the object 5 would have to be larger, either trailing on this side or on the other side. If it's leading, it would still have to be more massive. But either way, these would all be physical solutions. But before we continue, we need to ask, why haven't we seen a fifth clump? And this goes back to the question, well, why did we all of a sudden start seeing the 4 clumps in the D68 ringlet? And one idea is that there was impact from a debris field. And the debris field could have just gone through a certain region of this ringlet and stirred up dust around source bodies for 4 source bodies, but not 5, if it were in this sort of geometry. So it's possible that there could be a fifth one, and that could allow for more stability to this system. But even if there isn't, it could be a transient phenomenon. But if there is, we know where we can look for one. Anyway, I then continued with simulations using Mercury 6 as point masses for different mass ranges. And so with these initial positions, I just selected one position with the object 5 about 33 degrees ahead of the leading point mass. And we get a stable simulation. So this plot is showing time on the horizontal axis and a co-rotating longitude in the vertical axis. So just seeing all 5 horizontal lines here means that, sure, maybe it's a boring simulation because the co-orbitals all stay the same angular distance apart from each other. And this is the case if they are released at this exact stable configuration that is computed using the method of Rene and Siccardi 2004 for masses all the way up to about 10 to the 21 kilograms, which is on the scale of Saturn's moon Dione. Now, of course, if they were that massive, we would see them. But it just shows that it can be done all the way up to that mass for a stable system. Now, looking at maybe a more moderate mass case, if we scale them down to the mass of Daphnis, which is about 10 to the 13 kilograms, and we perturb their initial longitude, it's still a stable system. You can see that here with the initial positions a little bit more compact than what the stable solution says, they still oscillate around a stable solution. And so this is a stable simulation. If instead of a longitudinal perturbation, we give an initial perturbation in semi-major axis to 2 of the bodies, In this one, we released the second one 50 with a semi-major axis 50 meters greater than the semi-major axis of the rest of them. And we released the fourth co-orbital with the semi-major axis 50 meters smaller than the rest of them. This is still a small enough perturbation in semi-major axis for them to remain in a stable simulation. This system is stable. You can see that their co-rotating longitudes oscillate around the stable solution for these masses. And then this is for 1,000 years. But if we increase the semi-major axis perturbation to about 200 meters, now that becomes too much. And then this becomes unstable. They'd go on to horseshoe-like orbits. And so they would not maintain the same angular separation in this scenario. But what about for the masses we actually expect to be there? Because if they were as big as Daphnis, we would probably have seen them as well. So if we go down to 10 to the 8 or 10 to the 9 kilograms for their masses, which is what we might expect to actually see for the source bodies, even by making a semi-major axis perturbation of 1 meter, that's already too much. And yes, the simulation is longer because it takes a longer time for that difference in semi-major axis to allow them to interact with each other. But you can see that this configuration is unstable. And after a couple thousand years, they perturb each other and go on to different orbits. And so if we wanted to actually look at making some equation that would help us predict how much of a semi-major axis perturbation we can make and allow the system to remain stable, we can do that. And so this was done using lots of different simulations, probably a few hundred, at these different masses. And this plot is on a log-log scale. And so when we fit a linear best fit line on a log-log scale, there's really an exponent if we were to linearize the relation. And so using this best fit line, we can derive this relation for this delta A crit allowable semi-major axis perturbation compared to the semi-major axis is approximately equal to, you can maybe, if you're doing a back of the envelope calculation, ignore this first term, it's close enough to 1. You can round this to just a square root. And so it's the mass of the clumps added together over the mass of the planet. And that taken to the square root. And this dot up here corresponds to this last simulation that I showed you. And you can see it's above the line in the unstable region. And so if we were to want to get it down to that line at that low of a mass, it would correspond to about 27 centimeters. That is extremely small of a difference in semi-major axis that is allowable for the system to remain stable. So some conclusions on this Saturn's D68 ringlet is that it's very fragile. There's probably an external force that's keeping the D68 source bodies in place. Otherwise, if we were to try to explain it on their own, well, with 4, the configuration is inherently unstable and they will disperse. So it would be a transient phenomenon. Or if there are 5 source bodies, it can only be stable if the 5th co-orbital is within a certain range of longitudes and the differences in semi-major axes between all the bodies is very small, less than 27 centimeters for the masses we expect. So that tells us about that one location in Saturn's rings. And you might have questions on this, but we'll save them for a few minutes from now. First, I want to go over this other location in Saturn's rings. and we'll talk about moons and ring arcs in co-rotation resonances. And we have 3 moons of Saturn that are in co-rotation resonances with Mimas. And these are Aegaeon in a 7-6 co-rotation resonance with Mimas, and as well as Anthe and Methone in 10-11 and 14-15 co-rotation resonances. We'll focus on Aegaeon here, but there are some properties that correspond to all of these moons and ring arcs. And we want to know how the moons and debris interact in a co-rotation resonance. And part of that is because we do see a lot of dust in these ring arcs, but it's certainly possible for there to be bigger boulders on the scale of 1 meter to a few hundred meters that could exist there that we just haven't seen. Aegaeon is about 1 kilometer across. And so smaller than that, there could be bodies that we just haven't seen that are interacting with these moons. And here's just another close-up of Aegaeon in the G ring arc, so you can see how it's a bright spot there in here, and it's just in the middle of this ring arc. So when we look at the gravitational field in the presence of an oblate body, what we normally might think of as a mean motion resonance gets split into 2 different types of resonances: the co-rotation eccentricity resonance and a Lindblad resonance. And these have different effects. So the co-rotation resonance is what will drive oscillations in semi-major axis while leaving eccentricity unaffected. Whereas the Lindblad resonance will drive variations in eccentricity but leave the semi-major axis unaffected. And we can see this as an example. This is from a simulation using Methone's geometric orbital elements. So here's a change in semi-major axis. And the libration period on this is pretty short, just a year or 2. As well as we can see variations in eccentricity, which are driven especially when it is close to the Lindblad resonance, which is a little bit separate from the co-rotation resonance in semi-major axis, and that is done due to the to Saturn being oblate. Now, if we look at the co-rotation resonant argument of these 3 moons of Saturn, Aegaeon, Anthe, and Methone, of course, this phi will be defined differently. Phi is the resonant argument. It'll be defined differently for each of these moons. And Aegaeon is close to 180 degrees or pi radians. And that's because it's interior to Mimas, whereas Anthe and Methone are exterior to Mimas, so their resonant argument will oscillate around 0. But you can see that the amplitude is much larger for Anthe and Methone than it is for Aegaeon. That means Aegaeon is very close to the center of its resonance. And another fact about these is that Aegaeon is smaller compared to the rest of the mass in its own ring arc. And so we wondered if these 2 phenomena are connected. Could the fact that Aegaeon is comparable to the masses of the rest of the debris in its ring arc, could that be connected to it being so close to the center of its co-rotation resonance? Before we get into that, just another view of this resonance to help understand what it means is that we take the resonant argument, we rewrite it in this way so that we can say when the particle passes the moon here being Mimas, the particle being Aegaeon, or any particle in this ring arc, the 7 to 6 co-rotation eccentricity resonance site, then the mean longitude of the moon will be equal to the mean longitude of the particle. So this first term then is 0, because lambda m equals lambda. And so lambda m minus lambda is 0. So this first term goes away, and then we get the difference between the mean longitude of the moon and the pericenter, the longitude of pericenter of the moon, is approximately pi, or pi radians, 180 degrees, which means that the moon is near apocenter. So Mimas is near apocenter, the furthest away it gets from Saturn in its orbit, whenever it's passing, or whenever it's being passed, because the 7 to 6 co-rotation site is interior to Mimas. So whenever this particle is passing Mimas, Mimas is near apocenter. And so in a co-rotating frame of the 7 to 6 co-rotation eccentricity resonance, it appears that Mimas is tracing out this rounded hexagon shape in its orbit. And this is the result of this resonance. For every orbit that Aegaeon does, Mimas will go one leg of this rounded hexagon. And then, so first orbit, second orbit, third orbit, and so forth. And so for every 6 orbits that Mimas does, Aegaeon and the other particles in its ring arc will do 7 orbits. What helps us to analyze the the orbital evolution in a co-rotation resonance is this phase space, where we plot the semi-major axis along the horizontal axis and mean longitude, or co-rotating longitude, along the vertical axis. And so this plot is made from a compilation of different simulations where we only have 3 bodies: Saturn, Mimas, and 1 particle in the co-rotation resonance. And if we place it at the exact co-rotation resonance, it stays there. That's what this red dot is here. But if we place it starting a little bit outside of that, it'll trace out a sort of ellipse. In this one, it starts out 5 degrees behind in mean longitude. Because it's behind in mean longitude, it will feel a torque and will decrease its semi-major axis. And when it decreases its semi-major axis, it's on an inner orbit, and so it'll be going a little faster. So it'll catch up and pass in mean longitude, the mean longitude of exact resonance. But after it passes that, then it'll feel the opposite torque and begin to increase its semi-major axis. And as it's increasing that, it's slowing down. And then it'll, once it passes the semi-major axis of exact resonance, then it'll slow down and start to drift behind. And so this is, in phase space, it goes in a clockwise motion. And we can see these contours depending on where we release it in phase space. And these correspond to different energy levels, because in the view of the resonance, the center of the co-rotation resonance site is an energy maximum. And near the edge of the co-rotation resonance site, we can see that it kind of departs away from the sort of elliptical shape. It gets into a shape more like an American football. We're not going to go into depth about the fringe of the resonance. Its libration period also slows down near the fringe, but that can be for another study. So this ellipse is just drawn so that it's more or less outlines the phase space where the co-rotation resonance site is active. And outside of this ellipse, more or less, an object would not be in resonance with Mimas. So what happens then if we introduce multiple bodies that will interact gravitationally in a co-rotation resonance? What we're going to find is that they will have close encounters with each other. So what happens during these close encounters? Now, close encounters will happen whenever these two moons, or these two bodies in the co-rotation resonance, share the same mean longitude, meaning that they have the same same value along the vertical axis here. Because they are on eccentric orbits, even if they don't have the same semi-major axis, it's small enough of a difference that they do have encounters with each other. In the fixed frame of one of the bodies, the other seems to be going on this epicyclic motion. Each trip in and out would correspond to one orbit. Pericenter, apocenter, pericenter, apocenter, pericenter, apocenter, and then it's going to have a close encounter. And the outcome of the close encounter depends on whether it passes by, ahead, or behind the red body. So in the first scenario, we say the blue one passes by ahead, and then as a close-up, we could look at, in physical space, the blue body would feel a gravitational force pulling it backward, while the red one feels a gravitational force pulling it forward. And so as a result, the red one will gain energy, the blue one will lose energy. When the red one gains energy, its semi-major axis is increased. So its location in phase space will change. And as the blue body loses energy, its semi-major axis will decrease. And so also its location in phase space will change. Now, if we are treating the center of the co-rotation resonance site as an energy maximum, you can see that one particle or one body gains energy and one loses energy, but the total energy would seem to be conserved. But what happens if the blue body were to pass by the red body behind instead? If this were to happen, then the red body would feel a gravitational tug backward and lose energy. The blue body would feel a gravitational tug forward and gain energy. And in this scenario, the red body loses energy, which means its semi-major axis goes down, and the blue body would gain energy, meaning its semi-major axis goes up. And in this case, they're both moving away from the center of the co-rotation resonance site. And so it seems that energy is not conserved. So in reality, we cannot take this co-rotation resonance site center to be an energy maximum during these close encounters. And that's because the time scale of these close encounters is much faster than the time scale on which we consider this an energy maximum. The resonance, it takes time for it to act, and so it's not going to have as much weight to it during one of these close encounters. So some conclusions on co-rotation resonances then, when we have multiple massive bodies in them. Bodies in a co-rotation resonance exchange energy and angular momentum during close encounters. A body's semi-major axis can change enough for it to leave the co-rotation resonance site. More massive bodies have smaller changes to their semi-major axis, and so they would be less likely to exit the co-rotation resonance. They'd be more likely to remain. But none of this tells us that they should go towards the center, which is where we find Aegaeon. So there's, as yet, no good explanation, as far as I know, for Aegeon's presence so close to the center of its co-rotation resonance site. So just kind of wrapping both of these systems together, a big picture takeaway is that these co-orbital systems exhibit interesting dynamical behavior in their orbital evolution and seem to be finely tuned. Like if this, in this D68 model, the fifth co-orbital object, if it exists, would have to be at pretty much exactly the semi-major axis of the other four for it to be a stable system. And in the case of Aegeon's ring arc, it's still odd how Aegean is so close to the center of its co-rotation resonance site. So these two projects have led to two publications. If you want to dig deeper, you can look these up. The one I presented second was my first paper, Dynamics of Multiple Bodies into Co-rotation Resonance. And you can see it has one citation, and that's from Sylvia. So thank her for that. This second project that I talked about first, modeling Saturn's D68 clumps as a co-orbital satellite system, was just published 2 weeks ago. So it's a relatively new paper. So with that, I will end and can take questions.
Thanks for the presentation. Very, very clear. And let's see if we have any question. Anybody raise a hand or make a question, please? I have one. In this, I think it may be applied to both situations, the two systems. You have this clump of particles around, or in the case of Aegeon, for instance. And my question is the dissipative effect of the particles in that clump colliding or interacting with the satellite, with the moon, relevant? I think, could they be, for instance, the reason for moving it towards the center of the resonance?
Yeah, it could have some effect. Because the ring arc isn't quite as dense, I think the gravitational interaction could be more relevant. But in other cases, like with Neptune's ring arcs that are denser, I think collisions would have a more important effect there. But certainly they would happen in both systems, and it could have some dissipative effect as well. I don't know if that would be enough to explain how Aegean is so close to the center, but of course there's a lot more to this system than just one or two effects. And I know some of you have studied the dust in the ring arcs in more depth as well, and that's important too. So yeah.
Okay, good. So we have some hands raised here. So let's start with Sylvia. You can open your mic and make the question.
Sorry. Nice talk. I have a question related to the D68 ringlet, and it's about the debris. Could you show the slide, please?
Yeah. Let's see. Can I go to?
This is about the debris passing the ring.
Okay. This one?
You are not sharing
Oh, it's
your
stopped.
presentation now. Yeah, it stopped.
Is this the one you were talking about?
Yes.
Okay.
I miss it. This is the explanation? Is this the explanation for the formation of the moonlets or the clumps? I miss it.
This is the most likely explanation for the sudden appearance of the clumps. So,
the clump.
Yeah. What it means is that the source bodies were probably already there. We just didn't see them until this debris field passed through and stirred up the dust around the source bodies, because all of a sudden we saw a lot more dust. But they probably were already there. We just didn't see them before that.
Okay, thank you.
Mm-hmm.
Okay, good. So now Gustavo has a question, please.
Hey, Joseph.
Hey.
In the simulations of the clump, did you include the dissipative term that Henry considered?
Sorry, could you repeat that?
Henry 2006 considered a dissipative term in their paper. Did you include this term in your simulations?
I don't think I included any dissipative term. No, I missed the paper that you were mentioning.
Okay.
But yeah, either way, I didn't include a dissipative term in the simulation. So I mean, it is abstracted a bit from reality, and there would be more that's required to like fully explain the systems. But this is just looking at one aspect of it. Yeah.
Okay. Thank you.
Mm-hmm.
Okay. Any further questions or remarks? Anybody would like to make any comments? Okay, I think that's it. So
All right.
Thanks very much. I think it was very nice talk, very clear, and two interesting works. And as you said, they always raise new questions and new points to be included. But they are very nice. Thank you very much.
Thank you.